Welcome to my YouTube channel. In this video we are going to learn all the equations governing gravitation and see how they can be derived and how they can be applied. So the first thing we look at is a scenario where we have the Earth and another body. They are being attracted together. Now, the force of attraction of this body towards this Earth is given as Fg, and the force of attraction of this Earth towards the body is given as Fg. This Fg is always equal to this Fg. Okay, so this Fg is called the force of gravity, and the force of gravity is given by this expression Fg equal to GME m all over r squared, where r squared, r here, represent the distance between the body and this body. M here is the mass of the Earth that we are considering, and m here, this small letter m, is the mass of this smaller body. G is the gravitational constant. And one thing we must also know is that this Fg is usually equal to the mass times acceleration, while this one is also equal to the mass times acceleration, and which is given as Fg equal to the mass of the Earth times the acceleration equal to the mass of this body times the acceleration. But because the mass of the Earth is several times bigger than the mass of this, the acceleration of this is usually not felt, but the acceleration of this is felt because it is smaller. So this mass tends to move towards the mass of the Earth, and most of the masses that are being attracted to the Earth, they have a common acceleration, and that acceleration is called g, which is called the acceleration due to gravity. Okay, and that is given by g. This mg, which is equal to Fg, is also equal to the weight of this body. So the weight of the body is equal to this particular m. So instead of us to have ma, we now have mg. Okay, so this m can take care of this m, so we have g equal to this expression. So our r here, this g, is always equal to this expression, where r here is the radius of the Earth. So on the Earth surface, when the body is on the Earth surface, then this one holds. So we can also send this one to this side, and it becomes GME equal to this. Now, most of the time, instead of us to use this expression, we'll be using this one, because these ones are known. These ones are also known, but very difficult to remember them. And this one, at least we know, is 9.8. This one is 6,400 kilometer. So whenever we have a problem where we see a combination of this, we can replace with this one. Okay, so let's look at how the gravity is affected as you move away from the Earth's surface. And in that case, our RE becomes RE plus h, where h here is the altitude from the surface of the Earth towards any point. So it's given by this expression. So if we simplify this one by factorizing RE squared, RE out, we have this one. So our RE is out, leaving 1 plus h all over RE. Now we can square both sides. This one will be squared, this one will be squared. At this point, the g here will no longer be small letter g, which is the gravity. It will now be the new g as a result of the altitude, which is this one. Now remember that everything here GME over r is small letter g. So we have this g here. Now we can now see the connection between the g at a particular altitude and the g on the surface of the Earth. So this is our final expression. So you can see that when h is exactly equal to re, that is the height above the surface of the Earth, if it is exactly equal to re, what do you notice? The re and ro will cancel out, leaving it as 1. 1 plus 1 will give us 2. 2 squared will give us 4. So it will now be g all over 4. So when you are above the surface of the Earth and that altitude is equal to the radius of the Earth, you will experience 1/4 of the gravitational acceleration due to gravity. Likewise, if your H is twice this particular RE, you'll be having 2RE all over RE. RE will cancel RE, and you now have 2 plus 1, which is 3. That 3 squared, that will give us 9. So G all over 9, that will be the new gravitational acceleration due to gravity at that altitude. So as you go higher, there's a point where this one tends to become 0. So let's say this one is far high, which is approximately towards infinity. So everything here will be infinity. 1 plus infinity will be infinity. Infinity square will be infinity. G all over infinity will give us 0. So at that point you experience weightlessness. Okay, so let's see the next thing. So let's consider the potential energy under gravitation. So far we've looked at gravity and the connection between the forces between the head and the body. So let's look at the potential energy under gravitation. The common formula that we are familiar with is this formula, which is potential energy equals to mgh, right? But in gravitation we hardly use this formula, and the reason is because when you get towards when you move far away from the head surface towards infinity, the potential energy will be infinity, and in physics we don't want that kind of situation. We want a situation where we can get a value. So instead of using this one, we'll make use of this particular one. So our new PE is now minus GGE m all over r, where r is the distance from the center of the head to far above the surface of the head, right? So when we are very close to the head surface, this one holds, but if you are far away from the head surface, this one holds. And the reason why we have negative sign is because we want a situation whereby as r tends to infinity, the potential energy should tend towards 0. So 0 should be the maximum value, while anything below infinity, r equal to infinity, will take a negative value. Even on the earth surface, the potential energy should take negative value. In doing so, we will not have this ambiguity in potential energy tending towards infinity. So we know we'll have a value for potential energy far away from the head surface, which is at infinity, to be 0, while close to the head surface it's going to take negative value. So let's also look at the kinetic energy. Kinetic energy is given as half of mv squared, and we remember that the force holding a body in an orbit is equal to half of mv squared. Mv squared over r, which is given as F mv squared over r equal to gm this. Our m can take care of each other, our r can also take care of each other, so leaving our, or we can just take care of only the r, and that gives us we can divide both sides by 2, take care of our r, can take care of this r, so that you'll be left with mv squared over 2 equal to gmem all over 2r. Okay, so now we can see that this exact expression is equal to the kinetic energy, and this exact expression is now in terms of gmem all over 2r. So this will be the new expression of kinetic energy. So our kinetic energy is equal to either this or this. Most of the time, depending on what you are looking for, it is convenient to use this one, while sometimes it is convenient to use this one, right? So when we solve real life problem, we will see when to use both, right? So the next thing is to look for the total energy, which is also known as the mechanical energy of that satellite or the body above the earth's surface, and that will give us mechanical energy equal to kinetic energy plus potential energy, which is this one, which is the kinetic energy, plus the potential energy, which we already got without derivation. So if we add these two, we'll be having negative gmem all over 2r, because this one is half of this. So if you subtract this from this, you'll be getting a negative sign, and that gives us this. So we can see that the mechanical energy is given by a negative answer, right? Okay, so let's look at what our r is. Our r is the radius of the earth plus the altitude. You must take note of that. Always remember that r here is always equal to re plus h. Okay, so let's look at the velocity needed to put a satellite in a circular orbit. To do that, we must use the conservation of energy theorem to solve this kind of problem. So the first thing we look at is the kinetic energy plus potential energy when the body is on the earth surface. It must be equal to the kinetic energy plus potential energy when it is placed in that orbit, right? Okay, but in this case now, since we are asked to find the velocity needed to put, that means the initial velocity needed to launch it to a particular orbit. In that case, our kinetic energy will no longer take this kind of expression, but instead it will take half of mv squared. The potential energy will take something of this form. The kinetic energy, when it is in the orbit, is 0. Why? Because it doesn't move past that orbit, right? It doesn't move past the orbit, so it becomes 0. The potential energy will take something of this form with the equivalent r. So we have something of this form. So half of mv squared minus the potential on the earth surface equal to 0 minus the potential energy at that altitude where r equal to re plus h. So if we take this one to this side, we have this expression, and we can check that something is common between them. We can factorize out, and we are left with and take care of our m. So we have m goes out, then 2 comes back, and we have v squared equal to 2gme and this expression. So if we take the square root of both sides, we have this expression, right? So remember that we said anywhere we see g, capital letter G, capital letter E, M, E, we can replace with what? G, R, E squared, the radius of the earth squared. Okay, so and that gives us this expression. So you can either use this one or this one. Well, this one is the radius of the earth. This one is the what? The radius of the earth plus the altitude. Remember that. So that's that. So let's look at the next thing, which is the velocity of satellite in a circular orbit. The velocity of a satellite in a circular orbit is different from the velocity needed to place a satellite in an orbit. Know the difference between those two. This velocity is the velocity of the satellite in that orbit as it goes around the earth. That's the velocity. But this velocity is the velocity needed to launch it from the earth surface to that orbit. So know the difference, don't mix them up. Okay, so remember this formula, which is the total forces acting on the satellite must be equal to mv squared over r, right? So this is the only force that is acting on the satellite, which is equal to mv squared over r. So if we rearrange this one, making v squared the survey formula, we first of all have this, our m takes care of m, r takes care of r, then make your v the survey formula. We have v equal to gme all over r, and instead of us having this, we can replace with GRE squared, right? So this is the velocity. Now one unique thing about this velocity is that the r, right, depends on the velocity depends on the r, and for every value of r there is a corresponding velocity v. So if I have a particular satellite in an orbit r, let's say r1, then we'll have a velocity v1. If it is a little bit higher, r1, r2, then we have a little velocity v2. So take note. So all the satellites in this particular orbit will have the same velocity. We have the same velocity, and they can never meet. It's like chasing a particular person with a particular velocity, and that same person you are chasing has the same velocity with which you are running. So you can never meet the person. So in that case, the velocity of a satellite in an orbit is always the same for another satellite in that same orbit, and hence they can never meet. So please take note of that. So we move on to escape velocity. To calculate the escape velocity, we make use of our conservation of energy which is still k1 plus u1 equal to k2 plus u2. So as usual, this one will give me what? Half of mv squared. This one will give me minus gme m all over r, right? Now, because we really do not know at the point where the r will be, we take r as infinity, and because it is infinity, the kinetic energy will be 0. Likewise, this one, the potential energy at infinity is also 0. You remember we stated it, right? So anything below that value is negative. So this one will be 0, this one will be 0, and that leads to this expression. So if we take this part to this one, we have this expression. Remember, the kinetic energy as you go far away from the head surface will tend to have 0. So you can see the reason why we take our kinetic energy to be potential energy to be negative value, right? So that when you move towards infinity, you cannot just say this part will be infinity and this part will be infinity. It is more logical to make this one 0 when it is at infinity. Then anything below it, it's negative value, right? So when this one comes here, you have this expression. M cancels M, 2 goes up, make your V the Sebian formula. Then you have this expression, and V squared equal to this. Then finally you have this, V equal to 2gme all over r, radius of the head. Remember, we can also replace this one, and that will give us 2gme all over re, which is 2gre. Remember, this one is GRE squared. The RE squared will cancel one of this, leaving this one. So this is the velocity required to launch a satellite to infinity, right? Which is also known as escape velocity. So let's consider some velocities, some of the trajectories by certain satellites. Now, different trajectory of a body projected from the surface of the Earth can take this value v. Once your v is greater than the velocity or the escape velocity, this e represents escape velocity, then it becomes hyperbola. But if your v is exactly equal to ve, which is the escape velocity, then it's parabola. If v is less than ve, it is ellipse. While v equal to square root of gr is a circle. Please take note of this. This is a trend, right? This is a trajectory of any satellite that follows any of these equations, right? Okay, so let's look at parking orbits. First of all, we must know what parking orbit is. Parking orbit is a situation whereby a satellite in an orbit has the same period with that of the Earth, right? So in that case, we have this formula. We still make use of this formula, mv squared all over r equal to gme m r squared, right? So we can make our v the subject formula, v squared equal to this expression. But remember, for every object moving in a circular motion, there is this connection between them, between the radius, the velocity, and the period, which is given by this. This is the velocity, the radius of the circle, and this is the period. So this one is the period for a complete circle, right? This is the velocity with which it moves in that circle, and this is the radius. So the same thing can also be applied to a satellite moving around the Earth's surface. So now that we have our v, we can square this one and replace with this, and that gives us 2 pi r all over t squared. We can send this 2 here, or we open this bracket, that will give us 4 pi squared r squared all over t squared equal to this. So depending on how you want to do it, make your t the subject formula. T comes here, gme goes down, r comes up, which makes it r cube. Our t squared will come here, so if we take the square root of both sides, it becomes r 3 over 2. So this is the formula to find the period of a satellite in an orbit, right? You remember, we can replace this one with small letter g, which is acceleration due to gravity, times capital letter re squared, right? Once we know the altitude, we can find the what? The period. If you make your r the survey formula, we can also have this one. In this case, you might be interested in finding the altitude that will make the satellite possess the same 24 hours of the Earth. So what we do is to re-express this one in 24 hours, convert it to seconds, 24 hours, convert it to seconds, multiply by this, divide by this. That will give us this particular R. That R, once you launch your satellite to this particular R, when you have substituted all your values in, you will get a parking orbit. That is, the satellite will continue to remain in one position as it goes around the Earth's surface. Thank you. Hope you enjoyed this. Hopefully in the next the part 2 of this particular video, we'll come up with some questions, technical questions, and we'll solve them and see how we can apply some of these formulas. Thank you. Hope you enjoyed it. Please like, share, and subscribe to this channel. Thank you.